Good afternoon. Today we'll be taking linear programming, maximization of profit using simplex method. And we'll be doing that with this question here on the board. A company manufactures two products A and B using two types of resources, machine hours and labor hours. Each unit of product A requires 3 machine hours and 4 labor hours, while each unit of product B requires 5 machine hours and 2 labor hours. The company has a maximum of 60 machine hours and 48 labor hours available each week. The profit per unit of product A is 20 naira and the profit per unit of product B is 30 naira. Requirement: A. Formulate the linear programming problem. B. The optimal quantities to be produced, and C. The maximum profit. So we'll go straight to the question. Starting with A, formulation of the linear programming question. We'll start by getting the objective function, which will constitute the unit profits for each quantity produced, and then we'll go to the constraints. So the objective function will have two products that are being produced according to the question, product A and product B. So we are going to place them side by side, A and B. Then if you look closely in the question, they mention the profit per unit of product A to be 20 naira. So we are having, under A, we are having 20 naira, 20A plus, then we're having 30 naira under product B is 30. That will be P equal to 20A plus 30B. So this becomes our objective function. Objective function. We have our constraint is subject to the constraint. Our constraint is going to be formulated based on our question as well. Based on the question, there's a company manufactures two products A and B using two types of resources, and the resources, as we can see in the question, is machine hours and labor hours. So we're having machine hours and labor hours. Clearly, they say each unit of product A requires 3 machine hours and 4 labor hours. For product A, we are having 3 and 4. 3 machine hours, 4 labor hours. So, plus, we're only having, going forward, the stage, why each unit of product B requires 5 machine hours and 2 labor hours. 5 and 2. And less than or equal to. And say the company has a maximum of 60, meaning they can use 60 or less for machine hours. So less than or equal to 60 for machine hours. Then and 48 labor hours. So less than or equal to 48 for labor hours. Then we'll bring in our non-negativity constraints, showing that our answers for A or B must always be greater than or equal to 0. So we fulfill the first requirement, formulate the linear programming problem. Then the B says the optimum quantities to be produced. Start with the B, optimal quantities to be produced. For optimal quantities to be produced, we start by adding slack variables to the constraints we have available. So first adding slack variables. We are adding slack variables to the constraints. Adding slack variables to the constraints, we're having 3a plus 5b plus x1, which represents slack. First slack added is equal to 60. We're adding the slack variables so as to change our inequalities to equality. Well, 4a plus 2b plus s2 is equal to 48. After adding our slack variables to the constraint, we proceed to forming our table. This is our initial feasible solution. We are having basic variable, decision variable. Our decision variables represent our products, product A and B, product A and B. Then we'll have our slack variables. And finally, our solution quantity, abbreviated as SQ, solution quantity. For our slack variables, we'll have x1 and x2. x1 here, x2 here. Then we'll bring in what we call our profit row, our P row. Now, what makes this problem optimal? Based on what they have asked us, they said our optimal quantities. What makes it optimal is, in our profit row, once it's a maximization question, they don't want to see any positive values. We'll be having just negatives and zeros for us to reach optimality. So we are solving to achieve that level of optimality. Here we'll be having zeros and negatives in our PO. So I'll bring in the values we have here. We have 3 as the coefficient of A here, 5 as the coefficient of B, slack 1. So we have 1, no slack 2 in the first constraint. Then we'll have 60. Then we're having 4, 2, no slack 1 in the second, but there's slack 2, then we're having 48. Then we'll bring in the P row values, which will have 20, 30, 0, 0, 0. Then we can proceed to what we call getting our pivot row, our pivot column, pivot row, and pivot element. Our pivot column will get based on the maximum value in our P row. Our maximum value here is 30. So this makes up our pivot column, because here is 30, which is the maximum in our P row. So we proceed to getting our ratios, which will guide us in getting our pivot row. So for the ratios, we're having the solution quantity values being divided by our working column values, because this is called pivot column or working column. So we're having 60 divided by 5, and we're having 48 divided by 2. So we are calculating this. 60 divided by 5 will give us what value?
12.
60 divided by 5 gives us 12. Abi?
Yes.
So we're having 48 divided by 2
24.
gives us 24. So we're having 12 and 24. And what helps us guides us to get our pivot row is the minimum value in our ratios. And the minimum value in our ratios is 12. It makes here our pivot row. So this is our PR, pivot row, PR. The intersection between the pivot row and pivot column gives us our pivot element, which turns out to be 5. So I will abbreviate that to PE, pivot element is We will now proceed to get what we call the new row. In another table that we are going to be forming. Proceed to get the new row in another table. Our new row is simply our pivot row divided by our pivot element values. So our table here, we have a basic variable, decision variable, which is our A and B. We have our slack variable, S1, S2, and we have our solution quantity. So these changes are slack 1 value here because our pivot column is on product B and our pivot row is on X1. This changes to B and we still have S2 and our B row. So this constitutes our new row. Our new row is simply pivot row divided by pivot element. And our pivot element, as we have initially gotten, is 5. So 3 divided by 5 is simply going to give us 3 over 5. If we don't want to work with decimals, 5 divided by 5 is 1. 1 divided by 5 is 1 over 5. Then 0. 0 divided by 5, 60 divided by 5 gives us 12. We proceed to row operations to get our new value for S2 and S3. Here is our row 1, row 2, row 3. So based on the rule, our initial working column, once we have gotten 1 as a value in the working column, which represents here, the remaining values in that working column ought to be 0. So we are applying row operations that will help us get 0 in the remaining values that makes up the working column. This is our pivot column or working column, which is in this position of B. So we have a row operation here for row 2 and row 3 that helps us get zeros in our working column. So that will be row 2 divided by. The easier way to find out what we are going to be attaching to our new row in our row operation is simply going back to the initial table to find out what value we have in that corresponding position, which we are seeing as 4. So that will be row 2 divided by 4 new row. Two new rows, sorry about that. Row 2 divided by 2 new row. In our working column, we are having 2 new row. Row 2 divided by 2 new row. So we are having row 2 divided by 2 new row. Our row 2 values as we have here is 4201 and 48. 4201, 48. So our new row values we have 3 over 5, 1 over 5, 0, 12. To get our new values that will occupy our S2, 4 minus 2 into the bracket of 2 over 5 gives us what?
2 over 4 over 5.
2 over 4 over 5. 2 minus 2 into 1?
0.
0. 0 minus 2 into 1 over 5?
2 over 5.
2 over 5. 1 minus 2 into 0?
1.
1. Then 48 minus 2 into 12?
24.
24. That gives us our values here to be 2 whole number 4 over 5. We are having 0, 2 over 5, 1, and 24. For our P row value, we are applying row operation just as we have with the row 2 row operations. We are having a row operation that will give us 0 in our working column, just as we have demonstrated here. That will be row 3 minus the value we are seeing in that working column is 30. So row 3 minus 30 new row will help us get 0 in our working column. So row 3 values are 20, 30, 0, 0, 0. We have 30, 30, 30, 30, 30. Our new row values are 3 over 5, 1, 1 over 5, 0, and 12. 20 minus 30 into the bracket of 3 over 5 gives us which value?
2.
2. 30 minus 30 into 1 is 0. 0 minus 30 into the bracket of 1 over 5?
Minus 6.
Minus 6. 0 minus 30 into 0 gives us what?
0.
0. 0 minus 30 into 12?
Minus 360.
Minus 360. So this gives us our profit row values, which is 2, 0, minus 6, 0, minus 360. Now, this question clearly you can see is not optimal as at this particular table, because the condition for optimality is that all values in the B row ought to be either negatives or zeros. But we are having a positive value here, which is a positive 2. So we are going to do another iteration. Meanwhile, this is our initial feasible solution, while this represents our first iteration. This is our first iteration. Then we'll proceed to do another table, which we can call our second iteration, to see whether we will be optimal based on the condition for optimality discussed. So, wipe this. Before we proceed with that, we'll go through the same process of pivot column, pivot row, pivot elements before we form our new table. So our pivot column remains the highest value in our P row, which is positive 2. So this gives us our pivot column PC. We'll compute the ratios because of the space here. I think we can still squeeze it in. Call these our ratios. 12 divided by 3 over 5. 12 divided by 3 over 5. And we are equally having 24 divided by 2 over 4 over 5. This gives us 12 divided by 3 over 5 gives us what? Gives us
12 divided by 3 over 5.
12 divided by 3 over 5. 12 divided by 3 number 3 over 5 gives us what?
20.
20. Then 24 divided by 2 number 4 over 5.
8 whole number.
8 whole number
4 over 7.
4 over 7. And this gives us the smallest value for our ratio, it means that our 2 becomes our pivot row. Pivot column, pivot row, and our pivot element, which is the intersection of our pivot column and pivot row, becomes pivot element becomes 2 whole number 4 over 5. So we can proceed to get our second iteration. Our second iteration is our second table. We have our basic variable. We have our decision variable, which is products A and B. We have our slack variable S1 and S2. Then we equally have our solution quantity, which is SQ. So the B remains the same as we had from our initial table. So we have B. While our pivot column falls on A and pivot row falls on S2, changes our S2 to E. While our P row remains as P. We are going to carry out the row operation on our new row, which is this. So our new row is simply our pivot row divided by pivot elements. Pivot row divided by pivot elements. So 2 whole number 4 over 5 divided by 2 whole number 4 over 5, which is our pivot element here, gives us what? 2 whole number 4 over 5 divided by 2 whole number 4 over 5 gives us 1. 0 divided by 2 whole number 4 over 5 gives us 0. 2 over 5 divided by 2 whole number 4 over 5.
Minus 1 over 7.
Minus 1 over 7. 1 divided by 2 whole number 4 over 5.
5 over 14.
5 over 14. And having 24 divided by 2 whole number 4 over 5 gives us 8 whole number
4
over
over
7. So we'll carry out the row operations for row 1 and row 3. Row 1 and row 3. Since in our working column we have gotten 1, we'll be looking for row operations that will give us 0 in that same working column. 0 for this position and 0 for this other position. So row 1 minus, with the secret we've given before, we'll look for the value in that working column that will attach to the new row. So row 1 minus 3 over 5 new row. 3 over 5 new row. And we'll equally have row 3 minus 3, is it 3 over 5? 2. 2. Minus 2 new row. So we'll work out that row operation because of space here. We'll work out the row operations here and put in our values. Put in our values. For row 1, we have row 1 minus 3 over 5 new row. Our row 1 values, as you can clearly see, is what? 3 over 5, 1, 1 over 5, 0, and 12. We'll repeat our 3 over 5 based on the formula or row operation we have. Our new row values are 1, 0, minus 1 over 7, 5 over 14, 8 whole number 4 over 7. So we have 3 over 5 minus 3 over 5 into 1 giving us 0. Giving us 0. 1 minus 3 over 5 into 0
1.
is equally going to give us 1 here. 1 over 5 minus 1 over 5 minus 3 over 5 into 1 into minus 1 over 7.
2 over 7.
2 over
7.
7. 0 minus 3 over 5 into the bracket of 3 over 14.
Minus 3 over 14.
Minus 3 over 14. Then 12 minus 3 over 5 into the bracket of 8 whole number 4 over 7.
6 whole number 6 over 7.
Number 6 over 7. So we'll have that as the values here 0, 1, 2 over 7. As we have here minus 3 over 14. Minus 3 over 14. And we have here 6 over 6 over 7. 6 over 6 over 7. Then for our P row, we are having row 3 minus 2 new row. Our 3 values as we have here is 2, 0, minus 6, 0, minus 360. Minus 2, 2, 2, 2, 2 into our new row values 1, 0, minus 1 over 7, 5 over 14, into number 4 over 7. What are the values? 2 minus 2 into 1 gives us 0. 0 minus 2 into 0 is equally 0. Minus 6 minus 2 into minus 1 over 7 gives us what?
Minus 6 whole number
Minus 6 whole number
2 over 7.
2 over 7. Then we have 0 minus 2 into the bracket of 5 over 14.
Minus 5 over 7.
Minus 5 over 7. 3 minus 360 minus 2 into the bracket of 8 whole number 4 over 7.
Minus 377 whole number
377 whole number
1 over 7.
1 over 7. So that gives us 0, 0, minus 6, 2 over 7, minus 5 over 7. We'll have minus 377 1 over 7. So looking at this, you can clearly see that we are now optimal after the second iteration. We have zeros and negatives making up our period, so we can fetch our optimal quantities. You can see our B and our A quantities. Then we can equally figure out what is our maximum profit. So we'll do that in this base. So our optimum quantities as acquired by equation, optimum quantities for product B, the firm is advised to produce 6 whole number 6 over 7, which can be approximated to be 7 units. While for the product A, based on them being limited by resources in machine hours and labor hours, are advised to produce 8 whole number 4 over 7, which is resulting approximately 9 units of the product. So optimal quantities are B 7 units and A 9 units. Then maximum profit. For the maximum profit, we can easily pick out this value, or we can substitute into our objective function. So our objective function is simply B equal to 20 plus 30b. So that will be 20 into 9 plus 30 into 7. 20 times 9 gives us what?
180.
180. 30 times 7.
210.
210. We add them together, we'll have what?
390.
390. That will be approximate. That should be because of these are approximated values. Our approximated values. I think we'll be working with the values instead so that we don't confuse the whole thing. So if we work with the approximated value, with the fractional values that we have, our profit will be. So we are going to be substituting, instead of using these approximated values, using our fractional values in order to see that we can arrive at this value here. In order to see that we can arrive at this value here. So we're having 20 into our A, which is 8 whole number 4/7, plus 30 into our B, which is 6 whole number 6/7. So 20 into A gives us what?
171 whole number.
71.
3/7.
3/7 plus
205 5/7.
205, 205,
5/7.
5/7. If added together, we'll have what?
377 7 whole number.
1/7.
7.
So that gives us our maximum profit. So the requirement A telling us to formulate the linear programming problem solution. B asking us for optimal quantities which we have gotten. Then C asking us for maximum profit, which is this. This is our maximum profit. This question helps our students that are doing their ATS2 quantitative analysis under the topic linear programming. This can help them understand better their linear programming complications that I've been facing. This is also relevant to those doing performance management in the skills level of ICANN, for them to get under limiting factor where you have multiple constraints under limiting factor that leads to linear programming. This can come in handy to them too. Thank you very much, and remember to subscribe to the channel and turn on the bell notification. Thank you.